I probably should have recorded that. That would have been cool for everyone else to hear too. But that's the benefit of showing up. You get that little motivation. For module 2, we're going to be talking about water, soil formation, and then kind of how we classify soil. The notes are posted online. I have finally uploaded the student version of that, and I will try to get better at getting the rest of those uploaded so that students can print them. I will also open it the night before class, so the next module starts. I had a student who was high speed last night and said, hey, I want to print these notes, but they won't come up. I'm okay with you telling me to do that. Like, I don't know if sitting in my office at home that it's not working on your end. So I'm cool with emails, text. I had some people call me this weekend saying, hey, I didn't know we had a test today. I'm okay with all of that. So the notes are now available. I did print these out today so that you could at least be able to take some notes. Printing sucks, costs a lot of money. So I would encourage you to only print the slides that have stuff that you need to take notes on, which is what I did for this set of note slides. And so I only have just a few pieces of paper. And then you can go back and view the slides later instead of wasting all your ink and all your paper and all your money. So, I will tell you that the best way to study for this exam is going to be go to Walmart and buy you a stack of note cards and cut them in half. This is going to be a lot of memorization and some information, and I will try my best to figure out how to make it applicable. But the best way to study for this test is to get note cards. All right, so the big deal about water, we need it. That's the big deal about water. It has this molecule and this structure that makes it polar. It is a bent molecule, and that allows it to form bonds with A, self, and then also B, other substances or materials or things of that nature. And it's also a solvent and a dissolvent, so we need it. It is super important, especially in soils. And so one thing is, yes sir, oh, gotcha, Riley. I have one extra, it's perfect. Here you go. Cool. So I kind of set up soil structure and texture so that we know, and bulk density, because that is going to affect our pore space. So if we try and cram more soil into this core, we are decreasing the pore space. And if we decrease the pore space, we decrease our water holding capacity and our infiltration. We increase runoff and a whole list of other things. So you might hear this term tortuosity. And all that means is that it takes a lot to walk down here, and then up there, and then back down this row, and then maybe over here, and maybe every once in a while I can slide over here. So tortuosity is kind of the twisting and turning of the path of water and the flow of how it gets from the top of the soil to the water table. Because it's not just perfectly straight down, right? So our structure, our platy structure, remember the ones that sit on top of each other, so that water has to travel. That is the tortuosity of the soil. And those pores are all connected. And so that as our pore size gets smaller, the surface area actually increases. There is this capillary action where water has the propensity to travel upwards against the flow of gravity. And probably the best example that I can give you of capillary action is when the water rises up your jeans. Even though you haven't stepped in a puddle, some of that water that you kick up, or as you're walking across the snow or the ground, or it's wet or whatever, you know, you might have up to about mid-calf, you might have this water that moves up your jeans. That's capillary action, moving upwards against gravity. And it's all because of adhesion and cohesion. And so adhesion, much like adsorption, is the attraction of something to an unlike surface. Just remember that because it's adhesion, that it can also fall to the ground. It can also come off of that surface as well. Next, cohesion is the adhesion to like water molecules. And so when I think of cohesion, I think of the movie 300. And they all together, and they had their shields, and they all moved together as one unit. And so cohesion being attracted to the same molecule. And so, because adhesion and cohesion exist, y'all have plant science yet? No?
I did.
You did? So xylem and phloem. Xylem is from the soil to the leaf, right? How does the water get there? Partially adhesion and cohesion. Like it has to attach to the wall of the xylem, and then it will move up, and the xylem being this very thin tubular structure, it is able to move and rise along with matrix potential to move out of the leaf throughout the stomata. And so there's all these things going on that is removing the water from our soil. And so here's a look at basically on the left, this tube for A, that the thinner the tube, the greater the capillary rise, because the forces of adhesion and cohesion, they're so tight together. Like they're literally, the molecules are almost right up next to each other, and they're able to, like at some point, you kind of almost get like this squeezing action, and there's so much water that it has to go somewhere, and it can't bust out of the cell, so it goes up. And then also movement by capillary based on structure and texture. And so that's why texture by feel was so important, because you can do texture by feel and know that it's a sandy loam and go, I'm probably not going to get very much water holding capacity out of this, and it's probably not going to move very much. It won't move up against gravity, but gravity will force it down. Or you have a silty clay loam where the pore spaces are so small and so connected that water can rise up. It may take longer, but the water can rise to the top. And then finally on the right, just showing how long it might take for water to rise. And so we see that at sand, for a sand, it will rise very quickly. I will try and find a video of this. I actually had to do this for my master's. The water rises very quickly in sand, up to a certain point, right up to a certain height, because the capillary rise just won't allow it to continue on. And so I had these little rings. Maybe we might do this in lab, and we put them in water. And you could actually watch the water rise from the tub to the top of the ring in the sand very quickly, a couple of seconds. But it took the clay a little bit longer, because it had all those little pores that it had to fill first, and the tortuosity, that it took a long time, or a longer time, for the water to fill the pore spaces as it moved up the tube. Tube being pore space in soils. So the smaller the pore space, the greater the capillary rise. The larger the pore space, the lower the lesser the capillary rise. I have problems with using greater and lower and higher and all those things like that. Those capillary forces, again, mentioned by pore size, but also how much water is available. So in our clay loams, we have a greater available water compared to our sand, just because it can't hold as much. And the reason for that is because think about a sand particle versus a clay particle. We'll have more clay particles in there, but there's more pore space, so it can hold more water. Kind of like an ice cube. If you don't have an ice cube in there, you can fill the glass pretty full, right? Almost the whole volume. But if you have ice cubes in the glass, you only get so much water in there. Same principle with soil. In a given area, we only have so much sand and silt and clay that we can put in there. And if sand is the predominant particle, we can't hold as much water because the sand's taking up all the space. So, in soils, we have 3 measurements of how we determine how much water is there. Saturation makes sense. All the pores are saturated. That's 100% filled with water. Next, we have field capacity. So it rains, and it rains hard, and your field might flood. The water has to go somewhere. So based upon your slope, the water either runs out the ends to the ditch, or it has to go downward. Much like a glass, if it's full, it can't go anywhere. So there's this, gravity starts to pull that water down through the soil profile, and at some point in time, no more water is pulled through that profile. And so we call this field capacity. And this is measured at negative 0.1 to negative 0.33 bars, somewhere in that area. And then finally, permanent wilting point. Now, the thing about permanent wilting point is there may be water still in the soil. There may still be water there, but the plant cannot pull it off the soil column. So while there may be water, the plant can't absorb it into its system, and it dies. Alright, so I'm going to work from the bottom to the top here. But I do want to point out, you did notice that as the numbers become more negative, the water content becomes less, right? So at saturated, it's 0. At field capacity, we get a little bit more negative. And then at permanent wilting point, we are really negative. Okay? So let's start with permanent wilting point, this being this sponge. Don't have sponge sit outside too long, and then you go try and use it to wipe something up and it doesn't work. Right? Because all the water's out of it. There's no water left in it. It's a brick. And so that's kind of where this sponge is. This would be at permanent wilting point. There might be a little bit of moisture in there, but not a whole lot. Okay? So the sponge being at permanent wilting point. Oh. it rains, we fill all the pore space up. I don't know why they use these. I'll be all right. Won't be the last time I get wet, right? And so at this point, we are saturated and gravity is pulling that water through the sponge. Sponge isn't doing anything. Am I getting this? I hope they got that on video. I bet it did. So there we are, gravity pulling all the water out. We'll speed this up a little bit just for demonstration purposes. Not much more water coming out of that. So now we're at field capacity, right? So we were at permanent wilting point with no water in there, bone dry, what we call that. And then we were saturated and water is coming out the bottom. So that is, there's still a little bit of water coming out because water weighs how much? Anybody know? 8 pounds per gallon. Yeah. So if you ever need some weights, just fill up a 1 gallon jug and you've got 10-pound weights. Doing some curls. Once we have all that water out of there, just pulled by gravity, now we're at field capacity. Now the plant has this water to work with, and the nutrients that are in the soil are going to be dissolved in the liquid. When the plants take the liquid up, they also take the nutrients up. That's how they get into the plant. Okay? Clean my mess up. Finish that. And so, the long and the short of this is that water moves from areas of high content to low content. And so much like the sponge that I had, when I added the water from the top, guess where it wanted to go? One of two places. Evaporated or all the way through by gravity. And since in soil we don't have anything down here, going the other way, we're trying to get to the area of lowest concentration. And there's not a whole lot of water in the air, is there? Now there's some. We do have humidity and there is moisture, but if we're saturated in our soil, eventually that water is going to go down. At some point it will stop, but it needs to go somewhere else. And so it will travel up the plant, through the top of the plant, and then be exited out in the, through the stoma. Stomata. So we're in the soil right here. We have our water saturation. At some point, the plants are going to take that water up, and then it will move up the xylem through cohesion and adhesion, and then finally will be transpired out of the plant and into the water. And so going the other way, you will notice that the potential is becoming more negative. A demonstrator, or just a picture showing that we're saturated at 0 bars. Some of that water moves down through gravity. We're now at field capacity at about negative 0.3 bars. And then finally, permanent wilting point somewhere between negative 10 and negative 15 bars. After that, it doesn't matter. It doesn't matter if it's 16 or 32. That's the max. It's done. There's no more water left to be taken up. But you do see that we do have a little film of water still adsorbed around our soil colloid. It's just that now the soil, remember that the attraction, the aluminum, or let's say the magnesium, or whatever it is, the electrostatic hydrogen bonding is now to the soil colloid and not just free and floating in the solution. So, this graphic is just showing the soil water content. We started at about 50%, because remember we have about 50% pore space and 50% mineral space. And remember that varies between, the ideal soil has how much air space? Excellent, 25%. So if it has, guess how much water space can it hold? The ideal soil, 25%. So if we have all air or all water, that's about 50%. And if we have all air at permanent wilting point, about 50%. So the water content will decrease as our soil moisture potential starts to become more negative. Water content decreases as soil moisture potential becomes more negative. And then along the right kind of has a little bit of information kind of showing you where we have the gravitational water because we're at saturation. This is available up until about 10%, and then we will also be decreasing down to our permanent wilting point right here. And anything past permanent wilting point, the water is unavailable. It's not that it doesn't exist, it's just not available to the plant. We typically don't want to get here. We will put some irrigation on before this gets there, right? Because we don't want to cross the dye with any water, just like us. And we dehydrate at some point in time, we have to stop and can't do anything because we've lost all the water in our system. So you can kind of relate our human body to plants as well. We're both transpiring some moisture through work. All right. Not that this is going to be a very, like an equation that you'll have to remember, but just to have an understanding of all the forces that go along with getting that water from the bottom, from the soil, all the way to the top of the plant. And y'all, we keep it pretty simple. So this is psi, PSI. Y'all know the symbol. We got some Greek in here. Psi. G for gravimetric. S is going to be solute or osmotic potential. This is going all the way back to like biology class, right? Diffusion, concentration gradient, salts, osmosis from high concentration to low concentration. We have matrix adsorption forces. This is from our soil. So this is the attraction of the water to soil, or whatever other matrix is there. It could be wood bark. If you were in a nursery situation. And then finally, pressure. And so that is also going to go along with gravity. Because the more water we have on top of other water, right, it still weighs 8 pounds per gallon. So it's pushing down on the water below it. Just that as the water above it becomes less, start getting into some velocity stuff right there. And then also there's like air pressure too. So that plays another part into it. If you were to go into soil physics, don't do that. there are other forces and things that other scientists study that have some implication on how water moves in a soil profile. This makes sense, right? Because remember, when we had saturation 100% full, the potential was 0. That as we lost the gravitational water and we're now at field capacity, we're at negative 0.1 to negative 0.3 bars. As we lose more water to plant uptake through some evaporation, through some movement through the profile, we become at permanent wilting point, negative 10 to negative 15. For the purpose of this class, we will always talk about bars. I know you might look back at some of those other slides and it may be in pKa or kPa or atmospheres or whatever. Y'all's just multiples of 10s or hundreds, depending on whatever the scale is. But for this part, we're going to talk about bars. So when I ask you what the permanent wilting point is of soil, bars. I don't think I had anything to write down in these, but just to kind of show you that when we have that big equation on where this can be positive and where this can be negative. So gravity exerting a pulling force from the bottom, gravity pulling that down is a positive number. At some point, it's rained. We've saturated all the pore space. The gravity water's been pulled out. We're now at field capacity. And the water is in the water table, right? It had to go somewhere. At some point it's going to reach bedrock and it won't be able to go anymore. Saturated, gravity is a positive force pulling down because water's heavy. It's 8 pounds per gallon. At some point, there will be no more gravimetric pressure because the water's all falling out through gravity. But because of capillary rise, the water can begin to move back up into the soil profile. That is a negative value. Why? Because we're trying to move from an area of high content to low content. Remember, it's always trying to get to the area of least content, which is in the atmosphere. It's part of the hydrologic cycle. So that water can begin to rise all the way back up that soil profile if the texture's right. Probably not going to happen in a sand, but it might happen in a silt lump. Just depends on the texture. So we have these two things going back and forth, one to the other. It floods, water falls all the way through, plants use all the water, we get to about, I don't know, let's say -7 bars. Getting close to permanent wilting point, the plants will exert some force, this sucking force, to start to pull some of that water up. So it's trying to get more negative. The potential in the plant is more negative than the potential in the soil. And so that will rise back up. Maybe not all the way, but you guys understand the point, right? Tie this thing to my wrist. Osmotic potential. Did I skip one? This is the movement of based on solutes. And so if you have more salt in the plant, water will move into the plant because it's trying to get that equilibrium. If you have more salt in the soil, guess what happens? It's going to go to the soil because the water, because the matrix potential is more negative in the salt area. We're talking like right around the plant root. So if you apply a whole bunch of fertilizer and your plants die, not because you over fertilized. The salt concentration was so great around the root that it sucked all the water out. So there's a balance between there, like that's why we apply it with water. If you apply too much of it with not enough water, you're going to burn stuff. The matrix potential, again, is what is adsorbed to the soil. And so the drier the soil, the more negative the matrix potential. Remember, we're always trying to move to areas of low, or water's moving to areas of more negative value. So the matrix potential of a soil particle would be very great. That's why it holds on to that little very film of water surrounding it. Because the matrix potential is so great, negative 10 to 15 bars, compared to negative 0.1 or negative 0.3 bars. And then the pressure potential, which is what I mentioned. When you have when this is fully saturated, the pressure of the water is pushing down on the water below. So now we have pressure potential and gravimetric potential trying to pull that water down. If it's unsaturated, the pressure potential is zero because there's nothing on top of it. There's no water there's no pressure. Again, back to this figure that we have water moving up the plant and then finally out with our potential being negative 100 volts. Just that water is moving to areas of more negative pressure potential. I think we remember this from lab that sands are going to hold less water than silts and clays, right? We didn't take as many squirts to get the sand wet. But we took a lot of squirts to get the clay wet and moist and kind of fill all that pore space. And then finally down here, that when the water potential becomes, the soil water potential is more negative, texture doesn't matter anymore. It's going to continue, it will always continue to permanent wilting point, regardless of the texture. It's the time it takes to get to permanent wilting point. But the potential is still the potential. Permanent wilting point happens at negative 10 to negative 15 bars in every soil. It just might take a longer time to get there in a clay versus a sand. Because sands don't hold on to water as tightly, but clays do. So there is more water to kind of buffer against getting to negative 10 to negative 15 bars. Here we are, permanent wilting point along the bottom, negative 10 bars, and it's the combination of all of the potentials together. All that's really saying. Does anybody need this still? There's just a couple of methods that we use to measure soil water. You might run across these in the field. We do gravimetric, and so when we were in the lab, if you remember from the very first bulk density lab, I gave you the mass of the fresh, or the mass of the field capacity. That's if we go out and take a soil sample, there's water in that sample, we put it in the oven and dry all the water out, so that we're only left with pore space and mineral space. Well, we can measure the content and how much that weight, mass of the fresh versus mass of the oven dry. Once we in that one little sample, when we figure out the mass of the water, we can figure out how much water is available. So I can go out to a field and collect a bulk density sample and take it back to the lab, and within one day, as long as it's dried out, I can measure the pre and the post, and I can start to tell you how much water you have in the mat based on the mass of an acre furrow slice, just from one little 3-inch core. So that's one way that we can do that. Other ways that we can do that would be this time domain reflectometry. We did a lot of this working for a master's student. It's just a probe. It tells you what the content is. It measures the electrical conductance across those three poles. Kind of like anybody have the scale where you stand on it and it gives you the water content and how much the body mass index? No. I got one of those because I need to know. My fat ass needs to be I'm trying to lose some of this for the summer. But anyhow, I have one of those scales that tells me how much I have, how much water weight that I have, how much muscle mass that I have, and how much BMI. So they measure it the same way. They send waves up your body that you can't feel, and it measures the conductance in between all the water and all the muscle and all the fat in your body.